Hello. In this segment, we are going to talk a little bit about trade-off analysis. In an earlier segment, we talked about and discussed this concept of factor analysis, where we look at consumers' interest in a product and we try to determine a series of attributes or features that are important to the consumer, and those features or attributes become factors. Now what we want to do is be able to take those features and attributes and determine which ones are the most important based on the consumer preference. So we're going to apply something called conjoint analysis, where we have a product that is essentially broken down into many different individual pieces. Those pieces are the factors or attributes that the product can take on. So conjoint analysis is a technique that we'll use in order to break down or decompose a product based on consumer preferences, and consumers will make these trade-off decisions. So they might want a lower price, but they're willing to sacrifice some efficiency or some other feature that the product has in order to get that lower price. And so they're willing to make a trade-off. The question that we have is, how much are they willing to trade off for one attribute in order to get another attribute? So conjoint analysis is a form of trade-off calculations when it comes to product attributes. So that's what we'll talk about, and we'll specifically focus on a couple examples that show us how conjoint analysis works. The topic for today's segment here is trade-off analysis, and in particular, we're going to focus on a type of trade-off analysis called conjoint analysis. Typically, when we look at different features of a product, we think of them as determinant attributes. And when we do perceptual maps and we do factor analysis, we are comparing oftentimes different determinant attributes to figure out which ones are the most important and how we perform specifically on those determinant attributes that customers feel are important to them. However, one challenge happens when we have multiple determinant attributes that we want to look at all at the same time. So one idea is that a product is a composite of many different features or attributes, and we want to be able to look at the entire product as a whole, which is the sum of all of its different pieces or features or attributes. So this can be a challenge if we're only looking at a perceptual map that has two features that are demonstrated at a time. A lot of times we want to look at more than one. So in trade-off analysis, one of the ideas is that consumers will look at products and they'll provide their preferences as to which products meet their needs the best based on the different features or attributes they have, and they're willing to trade off some features for others. So for instance, a product may work very fast, very quickly. It might be like a machine of some type that works very quickly. However, the price of the machine is higher than its competitors. And so the customer may be willing to make the trade-off between price and performance in that particular case. So the idea of trade-off analysis, or the technique we'll talk about, conjoint analysis, really focuses on this idea that we can take a product as a whole and then break down its different features and determine which ones are the most important and which ones are the most desirable for the customer. So in order to do trade-off analysis, then what we'll do is we'll provide our respondents or our consumers with a description of different products or different product variations. And then what we'll do is we'll ask the consumer to place in order their preference, most desirable version of the product, all the way down to least desirable version of the product. As we move forward, we're going to talk about two different types of conjoint analysis, something called a full factorial, and then a second version called a fractional factorial. And we'll talk about these a little bit more in just a minute. But a full factorial conjoint analysis is when the consumer looks at all the different types of products that could be offered or versions of a product that could be offered, and we have them rank, order each one. Okay, so again, we'll talk about those here in just a minute. The important thing is, though, in conjoint analysis, we want to be able to determine two different things. One, we want to determine which factors or determinant attributes are the most important. So in prior examples, we had different, like through factor analysis, we would come up with different determinant attributes or features, but we didn't always know which ones were the most important to the customer. This technique using conjoint analysis will tell us specifically which are most desirable. The second thing is, if we have various levels of each factor or each attribute, then we will be able to identify which of those levels are most important too. Okay, so conjoint analysis then finds optimal levels of each attribute of a product and optimal combinations of attributes based on the levels that are provided. And again, I've got some examples here coming up so that we can be fairly clear what we're talking about when we're looking at features and levels as well. Okay, so when we look at conjoint analysis, as I said, we'll have customers rank order their preference based on which products they like the most. Now here's an example of a hat or a bonnet, and they're all identical with the exception of color. So that's the only thing that is different, and we could ask consumers to take each one of these, there are 9 different hats, and place them in order from most preferred to least preferred. Now this is pretty basic and pretty straightforward. The products that are identified here only have one attribute of interest or one feature that's distinguishing, and that would be color. So after we collect data in this particular case, given that it only has one attribute, then we'll simply have the consumers rank order their preference, and the frequency of the hat that occurs the most often would be the most preferred color, and that's probably the color that we would first put into production. Since products, though, are made of many different attributes, this example probably isn't the most useful. Here's another example. This is a dating service example, and there are 4 images with some different varying information about the people that are in each one of these images. So the question is, how many different human dimensions are represented in this picture? And again, remember, what we're thinking is that a product is the sum total of all of its features and attributes. And so in this case, we have 4 gentlemen who have varying features. And what we would want to do is compare and contrast features by preference. So again, in this case, we have several different attributes of interest. Again, in a conjoint type of a test, we'd have people look at these pictures or images, and maybe they would be on a card or a piece of paper, and we'd have our respondents simply order the cards or piece of paper in the rank order or preference that they would have. If we have enough examples, and enough here, in this case we only have 4, but if we have enough examples of potential dates in this dating service, then we can calculate again how important each attribute is and what different levels of attribute is most preferred. So to get into this concept of attribute and level a little bit more, let's think about that dating service and the different characteristics that you could take out of those photos. There are 6 actually different dimensions that are identified in that dating surface example. Hair color, so we have, that's a dimension, and then there are different levels: light, dark, and bald, no hair at all. We have skin complexion or ethnicity: Asian, Caucasian, African, African American, Middle Eastern, Native, and so on and so forth. All right, so there are lots of different levels, and that's a second different dimension. Glasses, yes or no. They either have glasses on or they don't. Facial expression: smile, frown, happy, grumpy is kind of the look there. IQ, based on some standardized test scores, we have an intelligence or a IQ type level, and high, medium, and low are the 3 different levels there. And then location, and here we have geography specified. We had 4 different locations: New England, West Coast, Midwest, and South. Now, it's super important to remember a couple things. Number one is we're trying to distinguish or identify through preferencing which of these 6 attributes are most important, and moreover, an ordering of them. So 1 through 6, which is the most important, all the way down to which is the 6th most important. The second thing to remember that's super important is that in conjoint analysis, when we say level, we don't necessarily mean a ordered level. So like, for instance, hair color, we have light, dark, and bald. Those are just 3 types of hairstyle or hair color. It doesn't suggest in any way, shape, or form that one is more important than the other, or one is better than the other, or less good than another. They're just 3 different levels. Glasses, yes or no. Intelligence, high, medium, or low. Now that's interesting because that is an ordered effect. You can numerically measure high versus medium versus low. So there is an order of level in that particular attribute, but that's not a requirement by any means in terms of how this statistical approach takes. Okay, so we have we have 6 different attributes, and we have a whole bunch of different levels. Now, this is actually pretty significant. If you count up how many different levels we have for each different attribute, and then multiply those together, we get our total number of possible products, and in this case, dates, or different types of dates that could be had. So 3 different hairstyles times 7 different ethnicities times 4 different geographic regions times 3 different intelligence levels times 2 different glasses type times 2 different facial expressions comes up with 1,008 different and unique versions of this possible product. So what we're saying here is with 6 different attributes, and then all the different levels associated with each attribute, the different combinations or permutations that we could form would be over 1,000 different types of product in this case, or types of person that could be selected in the dating service. So remember we mentioned full factorial design earlier. What this means is if we did a full factorial design, then what we'd ask is for a respondent to place in preference in order all 1,008 different types of product version in this case. Now that's pretty unrealistic to do, right? I mean, most people can't even order more than 6 to 8 or so items, let alone 1,000. I mean, that would be impossible and impractical to be able to do that. So what we would rely on is something called a fractional factorial design, and assuming we have enough respondents to be able to do this, the different respondents would see maybe a handful or a variety of of different potential dates. And then if we had enough, again, if we had a large enough sample, if we had a large enough of respondents who were in the part of the study, then with enough randomness, we can still perform a conjoint analysis. So if we have a lot of features, and which means that there's going to be a lot of different product variations, then we'll typically do what's called a fractional design, and we'll split our potential products versions up across many different respondents. Here's another example. This is the Salsa example. We're thinking about a company that wants to produce salsa, and they have a couple different choices that they could choose from in terms of what is desired by the customer. So we have spiciness. So the spiciness of the salsa, and there we have mild, medium, and hot. So we have 3 levels of that attribute. We have the color of the salsa, red or green, and then we have the thickness of the salsa, regular, thick, and extra thick. So we have 3 different attributes, and we're actually going to have 3 times 2 times 3 again, right? So there's going to be 18 different possible salsa combinations, given the fact that we've got 3 attributes, 3 times 2 times 3. It's going to be 18 different product variations. And so customers then would be given either a description or some type of some card or some picture or some description of 18 different products, and then they'd simply put them in rank order. Now, once you collect the data, you can simply do a simple count. Which ones were most preferred versus which ones were least preferred. And here's the data laid out in a table where we have all 18 different possible varieties identified. So the very first line we have regular, mild, red. Okay, and that ended up being ranked 4th. And then we had regular, mild, green, which ended up being ranked 3rd. Now, just looking at these two, you can actually see, well, thickness is the same and spiciness is the same. The only difference was red or green, and green was slightly more preferred than red. So just, eyeballing this, we might say that maybe green is more preferred than red when all other things are equal. The question, though, is we want to be able to have some statistical way to show this and actually have some degree of measure so that we know to what extent green might be preferred to red. And quite honestly, we don't even know if color, red or green, is that important compared to spiciness or thickness. So we want to know which is the most important attribute, thickness, spiciness, and color. And then within each attribute, we want to know which level is more preferred there. We see the number 1 choice, the number 1 most preferred is thick salsa. That's mild, that's green. That was number 1 right there. The least favorite is extra thick, extra hot, green. So that's there. So extra thick, extra hot red was actually preferred in this case. So red beat out green. So we need to know a little bit more information. And so from these rankings, the computer will calculate something called a utility, or what is officially called a part worth for each level of each attribute. Okay, so each level of each attribute will be identified. Okay, so a part worth then is the estimate of utility, or the estimate of desiredness, I guess, based on the customer's underlying preferencing that they create after the data is subjected or placed into a software package. Now, this software package that you use, a lot of times we'll use SPSS, Minitab, SAS. You may be able to do it in Excel as well. You can do this by hand, but it's kind of tricky. There's no real reason to do this all by hand since we have statistical software packages that are readily available now. So what we want to do is allow the computer to take the preferences and then break down the preferences by attribute, identifying which ones are occur the most often and which ones occur with each other. And by doing so, we're able to get what's called, as I mentioned, the part worth. And it's just that. It's how much each part of the product is worth to the customer. So if we have extra thick, that's a level of the thickness attribute. Well, how much exactly is it being extra thick worth to the customer? That's what the part worth basically tells us. It's the utility or the value that has. When we sum up all the part worths for any given product, then we have the total utility that product would be worth to the customer with that combination in mind. Okay, so if we look at our data again, if we look at another table, we can look at specifically what part worths are relative to the 18 different product types that we have. So we have, in this column here, we have the thickness. So our thickness column is regular thick or extra thick. This column here is spiciness. And then this column here includes the different color. So we have a thickness part worth, which for regular is 0.161. So that's the part worth for regular, 0.161. Thickness, thick salsa is 0.913. So 0.913 is quite a bit bigger than 0.161. If you look at these, if you just compare these two here, so we could say that thick salsa is much preferred to regular salsa. And then we have down here, we have the extra thick part worth. That's negative. That's negative 1.074. So it actually hurts the chance that somebody will choose your salsa if it's extra thick. And so if we were to look at this, people most prefer thick salsa. And then we have regular salsa, and then people really do not like extra thick salsa at all. It has a negative part worth, so that hurts the likelihood that someone will buy your product if it's extra thick. When we look at spiciness, we have mild. So mild is 1.667. That's really big compared to these other ones. So 1.66, that's super big. We have 1.05 for medium hot. So medium hot is 1.05, and then we have extra hot, which is negative again. So if I had if I had extra hot salsa that was thick, that'd be a really, or extra thick. So I'd have this part worth, and I'd have this part worth. That would be a no-go right there. I already know that that's going to be a really bad product. People are not going to want that. That's going to be, because those are so negative. We'd add those negative scores together and it's just bad news. Whereas if I took a thick here and I took mild, then that's the beginning of a really good product because those part worths are pretty big. Okay, the very last part worth is color. And remember, we only have two. We have green or red. So when you look at this, one thing you might note, just as a side note, when you add part worths together, if you add them together, they'll equal 0. So they sum to 0. So we have a negative 0.161 and we have a 0.161. So green here is preferred to red. So if I had extra thick, which is this negative number, extra hot, red, that'd probably be the least favorite. In fact, it is. It's the least favorite product that I've got an offering in. If I have thick, mild, and green, then it'll be my most favorite. And what we do is we take our part worths and we simply add them together to get a total part worth or a total utility score. and then we rank order those total utility scores. So it's not the raw numbers that the customer's given us, like the most common just by frequency count. It's an actual calculation that's done to create a part worth through a regression formula, and then summing up our part worths to get some total utility to tell us which products are the best, or which products would be most preferred by the customer. Okay, so part worths then are super important in this conjoint analysis concept. There's a couple things to note too. These part worths are comparable. So like I see a 0.161 here and I see a 0.161 on color. These are like trade-offs. So this regular, having a regular thickness and having a red salsa would cancel each other out. I mean, they're comparable, they're sizable, they're standardized to each other. So they're comparable. So this is a way for us to compare levels equally and also attribute levels on the same playing field. All right, so part worth then is a number that represents the utility or the value that one level of one attribute has. Remember, products are bundles of attributes, so you can think of them as bundles of part worths. Adding together different combinations of attributes leads to different products, but it also leads to different utility levels based on the summed part worths that those attributes and those levels will provide us. Combining features that have the highest part worths essentially yields the most preferred combination of features, which kind of makes sense. Likewise, if you combine features that aren't desired, then you're going to get a less desirable overall product, because again, we're dealing with bundles of attributes working together. Okay, so another way to look at this, we can look at our part worth scores or our utility. So these are part worth scores on the side here, or our utility based on these different types of attributes. We see that this mild is super big. And this is relative to everything else as well. So if I'm going to get something right, for instance, if there's one thing, if there's one attribute that I'm going to get right, what I'm probably going to want to do is get this spiciness right, because that matters a lot. That matters quite a bit. Color, yeah, there's a difference between red and green, but its overall part worth scores they're not that great in magnitude. So it's like, if I get the color wrong, then it's not that big a deal probably. But if I get the spiciness wrong, then that's a big deal. That's a problem. Okay, so this is just another way to think about and look at how the attributes work. We can dig into this a little bit more. We can take the difference between the greatest and the smallest level within each attribute to determine which attributes are most important. So we know based on the part worth score itself which levels are most important. The question here is which actual attributes are most important. So I've got three different attributes: thickness, spiciness, and color. If I take the difference between the largest and the smallest, then I get this kind of overall range of part worth by attribute. Okay, this overall range of part worth by attribute. And remember, I said, color's probably not the most important, and it's the smallest. Spiciness is by far has the largest range, and so it's going to be the most significant of the three different attributes here. So again, I want to get spiciness right first, and then I want to get thickness, and then if I can get color right, then that'd be great too. Okay, so number one most important attribute, spiciness, followed by thickness and then color. And here's another little chart just to give you another illustration of how these go. 59.8%, almost 60% of the total value of the salsa is found in the attribute spiciness. roughly 35% is found in its thickness, and only 5.6% is found in its color. So again, like I can make the best colorful salsa in the world, but if it's not the right thickness or spiciness, it ain't gonna sell, because that one attribute, while we think it is important to the customer, in the end, it really isn't that important to the customer. And we can see that it only represents 5.6% of the preference that would be had in salsa categories. Okay, so some key points wrapping up here, this idea of conjoint analysis. You have to be able to break down a product into specific attributes that can be measured and identified. We want to be able to combine different features. So the customer needs to be able to distinguish different features that different products have. And it has to be something that is easily definable by the customer. Complex products that have way too many attributes might be difficult to do unless you can specify and make a distinction between the actual attributes that are there. This type of research is research. It's consumer research, and it's a stated behavior type of a research as opposed to a revealed behavior type of research. So we're not actually seeing buyer behavior, we're seeing buyer preferencing. So we're asking customers to tell us what they think as opposed to what they actually do. So that's a bit of a caveat with any of this type of research that we're doing. And likewise, since it's not a real buying situation, we don't have like true buyer behavior that's going on. Other things that are issues is if the product is a brand new to the world type of a product that had never been seen before, customers are going to have a difficulty being able to relate to it. So, you know, we have some assumptions that the product will be familiar to the customer moving forward. The example of salsa, as I've mentioned, is a full factorial or full profile conjoint analysis. That's not always possible. We mentioned the concept of fractional factorial designs before. So basically what would happen is a consumer would get a randomized or a subset of products to evaluate. Instead of all 18 salsas, they might get 9 salsas or 12 salsas. And the salsa choice would rotate by respondent if we felt like that was too many. There are more advanced methods that can be used to handle the interactions between attributes. You know, we assumed that there was no correlation between, say, thickness and spiciness, but there might be. It might be that some people prefer thickness like extra thick with extra spicy or something like that. There may be some interactions, in other words, that are happening that we can't pick up on. So there are advanced methods in the statistics of this to be able to cover for issues like that. Other issues that are more advanced deal with adaptive conjoint analysis. So basically somebody chooses a type of product that they like, and based on the type of product that they like, the version that they like, they answer other questions or other features as they go through the research process, the products that they get changes. And so sometimes when we do this, we can pick up on these the interactions between attributes that are desired to look at there. We also have choice-based conjoint analysis. So again, there are lots of different variations and extensions to standard conjoint that helps us do this. But ultimately what we're come down to is knowing that products are a bundle of attributes. We need to be able to identify what the determinant attributes are in advance. because that's what we're actually varying across our different product versions. Respondents need to be fairly well familiar or well known in terms of what the products are. So as I mentioned before, new to the world products are difficult to analyze. We want to be able to analyze the results and then deliver on products that vary on the different attributes that we're dealing with. So what if I was a salsa company and it turned out that I really didn't have a lot of ability to change the spiciness of my salsa? So that would pigeonhole me, or that would restrict me a little bit in what I could do moving forward. And in particular, knowing that spiciness is the most important attribute, then I'm going to have to be able to work on that feature either by gaining some new technology or branding myself in a special way. One final note is that, and again, this is an advanced conjoint analysis technique. Just because we know which features and which levels are most preferred, it doesn't take into account the cost of each feature or each attribute or level of each attribute. So we know that certain attributes cost to produce the product go up or go down depending on the level of the product feature. So presumably a machine that works faster probably going to cost more for us to produce. So an advanced technique is to build in a cost structure as well that will let you optimize how much of a level I should increase to based on the cost that I'm exposed to. So we can balance anticipated demand by maybe making a preferred product with anticipated cost that would result in producing the product with the features the customer wants. Okay, so again, that's an advanced feature of conjoint analysis, and it's certainly something that we want to consider as we move forward. All right, so wrapping this section up on trade-off using conjoint analysis, we're often struggling with balancing multiple attributes at once and having a system of equations to be able to calculate what the optimal product is. Conjoint analysis helps us deal with this. It breaks apart or decomposes a product into many different features and then different levels of the features and provides an actual score, a numeric score that shows how valuable each level of each attribute is. And remember, that's called a part worth or utility score. These scores are standardized so that they can be compared across each other. So when you raise one, you may be lowering another and so forth. So they're comparable and they're standardized. Approaches like this are very common nowadays. They help us put some numbers to the decision-making process when it comes to deciding what features we're going to add to our products. And it can make sense of a fairly complicated behavioral process that the customer goes through by letting the statistics of choice and discrete choice analysis actually determine what the customer prefers without relying on the customer actually stating that. Okay, so this wraps up then the trade-off analysis or conjoint analysis discussion in product development.